Ealvina with matrix number 206611. So this is my presentation for Fluid Mechanics 1 this semester. So my topics today is fluid properties and also dimensional analysis and modeling. So the first part of my presentation, I would like to explain a further more detail about fluid properties. So these are topics that we're going to cover in a minute. So Newtonian and non-Newtonian fluids, surface stretch and elastic modulus, compressibility of fluid, and vapor pressure. So before we get into our main topics, let's take a look at our introduction first. So fluids is a substance that continually deforms under applied shear stress or external force. Fluids can be either in liquid or gases, and some of the fluid properties are given here. For example, specific weight, density, specific gravity, surface tension, and viscosity. So fluids are substances with zero shear modulus, which means they are substances which cannot resist any shear rate. So the first fluid properties is density. Density is given the symbol as rho, and its unit is in kilogram per meter cube. So I've given here is the SI system. You can also change it to the US customary system, which is slug per cubic foot. So density is the amount of mass per unit volume of substance. Density is equal to mass per volume. Specific weight has the symbol gamma, and its unit is in Newton per meter cube. As I said earlier, you can also change it to US customary system, which will be pounds per cubic foot. Specific weight is the amount of weight per unit volume of substance. So specific weight is equal to weight over volume. So let's take a look at this relationship over here. So the relationship is between specific weight and density. So how do we derive this equation? So what you want to do is you want to times gravitational acceleration to the numerator and denominator. So then you will get this form. So you want to take out the weight per gravitational acceleration, which will then equals to mass times mass times gravitational acceleration divided by volume. And then mass over volume is our density here. So just substitute in rho here, you will get this equation. Specific gravity is the ratio of density or specific weight of a substance to the density or specific weight of water at 4 degrees Celsius. So the information for density or specific weight of water at 4 degrees Celsius is given here, as you can see here. So this is the SI system, and this is the US customary system. So just substitute in value and you will get the answer. Specific gravity is dimensionless because the unit cancel off each other and there is no unit. Moving on is the surface tension. Surface tension is the tendency of a liquid surface to shrink into minimum surface area possible. Surface tension acts somewhat like a film at the interface between liquid water and the air above. Surface tension is also measured as the work per unit area required to move lower molecules to the surface of the liquid. So its unit will be in Newton per meter. Because work per unit area. So work is in Newton and area is in, work is in Newton meter while area is in meter square. So these two cancel off each other and we will have Newton per meter. Specific volume is the number of cubic meters occupied by 1 kilogram of matter. So it has the unit meter cube per kilogram. Basically, specific volume is equals to volume divided by mass. So it's the opposite of density just now. Pressure has the symbol P and its unit is in Pascal. So we can derive Pascal into much more other units, for example, Newton per meter square. So pressure, its definition is amount of force exerted on a unit area. Pressure acts uniformly in all directions on a small volume of fluid. In a fluid confined by solid boundaries, pressure acts perpendicularly to the boundary. So let's see our Pascal's law here. Pascal's law states that a pressure change at any point in a confined incompressible fluid is transmitted throughout the fluid such that the same change occurs everywhere. So that is why we get our equation here. Pressure is equals to force per unit area. So the next fluid property is viscosity. Viscosity is the internal friction of a fluid caused by molecular attraction that makes it resist a tendency to flow. The first point here is given shear stress. Shear stress is denoted by the letter tau. Shear stress is a force required to slide one unit area layer of substance over the another, which means when two fluids are flowing, it produces shear stress. Basically, shear stress is the force divided by an area, which gives us the unit Newton per meter square. When a real fluid is in contact with the boundary surface, the fluid has the same velocity as the boundary. Now, real fluid means a fluid that possesses viscosity. So, when a real fluid is in contact with the boundary surface, meaning that when the fluid is closer to the moving surface here, the velocity should be same as this moving surface. While at the lowest surface here, the velocity should be 0. So if the distance between the two surfaces is small, then the rate of change of velocity with position y is linear, meaning that it varies linearly. Velocity gradient is the measure of velocity change and it is defined as delta v over delta y. And the proportionality constant gives us the Greek letter eta, which means dynamic viscosity. So that gives us the overall formula of this. Tau is equals to eta times the delta v over delta y. Velocity gradient is also known as the shear rate. There are two types of viscosity. The first one is dynamic viscosity and the second one is kinematic viscosity. Dynamic viscosity is denoted by the Greek letter eta and gives us the unit Pascal second. It is the measurement of fluid's internal resistance to flow. So as you can see here, this is the formula that we just saw. Shear stress is equals to dynamic viscosity times the velocity gradient. So I'll explain further more detail in the next topic, which is Newtonian and non-Newtonian fluids. Kinematic viscosity is denoted by the letter nu and gives us the unit meter square per second. So it is the ratio of dynamic viscosity to the density. Now I will explain about Newtonian fluids, which is our first topic. Newtonian fluids are fluids that experience shear stress that is linearly correlated to the velocity gradient. So what does that mean is that shear stress is directly proportional to velocity gradient. So this straight line over here, continuous straight line over here, is the Newtonian fluid, indicating Newtonian fluids. Magnitude of velocity gradient has no effect on the magnitude of dynamic viscosity, meaning that our dynamic viscosity is basically the slope of our Newtonian fluid graph. So when we take a point anywhere on this point, the magnitude of velocity gradient will not affect the magnitude of viscosity because the slope is constant. Dynamic viscosity will be constant at any point. Dynamic viscosity is a function only of the condition of the fluid, particularly its temperature. So, for example, here is when we take condensed milk, when you freshly open a tin of condensed milk, the viscosity or the texture of the condensed milk will be really loose and it's not thickened. But when you put it in the refrigerator for about few hours, then it will be thickened. Newtonian fluid obeys the law of Newton's law of viscosity. Tau is equals to negative dynamic viscosity times the velocity gradient. So I forgot to mention just now, dynamic viscosity can also be referred to absolute viscosity. So examples of Newtonian fluids are water, oil, gasoline, and alcohol. Non-Newtonian fluids are totally opposite than Newtonian fluids. Non-Newtonian fluids are fluids where viscosity varies based on applied stresses. So the formula is the same as the Newtonian fluid, but now eta is now denoted by apparent viscosity, which is a variable. Viscosity of the fluid is dependent on the velocity gradient, meaning that the velocity of the fluid changes along the slope. So the slope of the graph changes. For example, here we have our pseudoplastic here. So when I take a point and draw a tangent line to it, and also a point here and draw a tangent line to it, the slope will be different, which means the velocity gradient will be different for both of these. So I will explain furthermore about pseudoplastic in the next slide. So there's non-linear relationship between shear stress and velocity gradient, meaning that it is not a straight line. So it does not have a linear relationship. There are two types of non-Newtonian fluids, which are time-independent and time-dependent fluids. Time-independent fluids. There are three types of time-independent fluids: pseudoplastic, Dalton fluids, and Bingham fluids. Pseudoplastic fluids. The shear stress versus velocity gradient of pseudoplastic lies above the straight-line constant slope of Newtonian fluid. So the curve of pseudoplastic will begin steeper, which indicates a higher apparent viscosity, then decreases. Then the slope decreases with increasing velocity gradient, indicating lower apparent viscosity. So example of pseudoplastic is blood plasma. Second one is Dalton fluids. Dalton fluids, the graph of shear stress versus velocity gradient of Dalton fluids lie below the straight line, Newtonian fluid, which is this line over here, this continuous line. The curve begins with a lower slope, which indicates lower apparent viscosity. Then the slope decreases with increasing velocity gradient, meaning that it is totally opposite than the pseudoplastic. It will begin with a lower slope, then increases the curve will become steeper as the velocity gradient increases. So example of Dalton fluids is starch in water. Bingham fluids, also known as the plug flow fluids. So Bingham fluids requires a significant development of shear stress before the flow begins, and it will not begin to flow immediately. As you can see here, the value of shear stress is quite high, and it starts from a high value of shear stress. Then only it will start to flow. Once flow starts, there is an essentially linear slope to the curve, indicating a constant apparent dynamic viscosity. So this is the constant line, straight line here. which indicates apparent dynamic viscosity, indicated by the Greek letter eta. So example of the Bingham fluids could be ketchup. When you shake a bottle of ketchup, the ketchup will not come out immediately. So it requires a significant amount of shear stress for it to come out. Time-dependent fluids are difficult to analyze because apparent viscosity varies with temperature, time, and also velocity gradient. So that is why it is very difficult to analyze this. So I've provided two examples of time-dependent fluids here. The first one is thixotropic fluid. So before that, let's take a look at this graph. The y-axis here is the dynamic viscosity and the x-axis here is the time. The left part of the curve shows stable viscosity when shear rate is not changing. When the shear rate changes, the apparent viscosity also changes. Thixotropic fluid. The apparent viscosity decreases with time as shear rate remains constant. As you can see here, this is thixotropic graph. The apparent viscosity decreases with time as the shear rate remains constant. This is the line where the time at which the shear rate is increased. So thixotropic fluid are the most common fluid in time-dependent fluids. The next is rheopactic fluids. Rheopactic fluids, the viscosity increases with time. And these are quite rare. Surface stretch and elastic modulus. Stress. Stress is the quantity that describes the magnitude of forces that causes any deformation on a particular material or an object. So it's basically the force applied to a material divided by the material's cross-sectional area. So the symbol given to stress is sigma, and the unit is Newton per meter square or Pascal. Or you can also change it to US customary system. Sigma is equals to F over A naught, which means stress is equals to force divided by cross-sectional area. Pulling force on an object which causes elongation is called detention. So for example, if I take a pencil and I start to pull the pencil on both sides, that causes tension stress. The second one is when an object is compressed, it is called compressive stress. So when you take a spring and you compress it, and compressive stress is produced. The third one is when deforming forces act tangentially to the object's surface, it is called shear force, which causes shear stress. So the last one, when the object is being squeezed from all sides, it is called bulk stress. Strain. Deformation or displacement of material that results from applied stress. So stress causes strain. Strain is given by the equation strain is equals to length after load is applied minus original length divided by original length, or simply difference in the length before and after divided by the original length. Strain is dimensionless because the unit cancel off each other. Strain under a tensile stress is called tensile strain. Strain under bulk stress is called bulk strain. Strain under shear stress is called shear strain. So the greater the stress applied, the greater the strain will be. Relationship between stress and strain is not always linear. It only happens when the stress is sufficiently low. The deformation will be proportional to the stress value. Now, what does this mean is that when the applied stress to an object is right below the elastic limit, the stress strain graph will be linear. So elastic limit is the limit where after this limit permanent deformation will occur. The point at which the largest stress value can be obtained is the proportionality limit. The stress-strain graph is a straight line where the gradient is equals to the elastic modulus. So I will explain more about elastic modulus in the next slide. Beyond this proportionality limit is the elastic limit, in which stress is not proportional to the strain anymore. Elastic modulus. Elastic modulus is the quantity that measures an object or substance resistance to being deformed elastically, non-permanently, when a stress is applied to it. So just now I've explained that the gradient or the slope of the stress-strain graph is the elastic deformation region. So stiffer material will have higher elastic modulus. For example, wooden ruler and a plastic ruler. Wooden ruler will have immediately break into two pieces when applied stress is enough. But plastic ruler, it will not break in until the applied stress exceeds the elastic limit. So this is the difference between a plastic material and a wooden material. So elastic modulus is given by the equation stress divided by strain, which then gives us force divided by cross-sectional area divided by change in length divided by initial length. So where the stress is the force causing the deformation divided by the area to which the force is applied. And strain is the ratio change in some parameter caused by the deformation to the original value of the parameter. Since strain is dimensionless quantity, the unit of E will be same as stress, which will be Newton per meter square or Pascal. So there are three types of elastic modulus. So the first one is Young's modulus. Young's modulus measures the tensile stiffness of a solid material. Shear modulus describes an object's tendency to shear. This is defined as shear stress divided by shear strain. And bulk modulus, which we'll further discuss a bit more in the next slide. This describes the volumetric elasticity, and it is defined as volumetric stress over volumetric strain, and it is the inverse of compressibility. Compressibility of fluids. The first one, compressibility of liquid. Compressibility of liquid is the change in volume due to change in pressure. So we normally use bulk modulus of elasticity to measure compressibility of liquids. Bulk modulus is basically how much compressible is a fluid. Compressibility of a fluid is inversely related to its volume modulus of elasticity. Bulk modulus is equals to negative change in pressure divided by change in volume divided by volume. Because liquids are only slightly compressible, it requires a large change in pressure in order to produce a small change in volume. So the magnitude of bulk modulus for liquids are very high. Liquids tend to take the shape of the container. So we will usually assume that liquids are incompressible because it requires a large change in pressure to produce a small change in volume. Compressibility of gases. So gases, we will not normally use bulk modulus to measure its compressibility, but instead we use the principles of thermodynamics, which are used to determine the change in volume of a gas with a change in pressure. Gases has a lot of space in between the atoms, so it is readily compressible. Usually, we assume all gases are perfect. Perfect gases are also ideal gases. Perfect gases are defined to have constant specific heats and to obey the perfect gas law, which is the given equation, where the absolute pressure divided by density is equals to the pressure times the specific volume, which will then equals to a gas constant, which the value depends on the particular gas, times the absolute temperature in degrees or Kelvin. Vapor pressure. Vapor pressure is the measure of the tendency of a material to change into the gases or vapor state. Basically, vapor pressure are pressure exerted by a vapor when the vapor is in equilibrium with the liquid or solid form or both of the same substances. So as you can see the picture on my right side, let's assume that this is a cylinder and it is closed with a lid. So when there is a lid on the container, the gas phase molecule are trapped. So they are a vapor now. So this vapor will now create a vapor pressure. So that is what we call vapor pressure. Vapor pressure increases with temperature, and its boiling point of the liquid is the point where the pressure exerted by the surrounding equals to the pressure exerted by vapor. So these are the factors affecting vapor pressure. The first one, surface area. Surface area do not give an effect for vapor pressure. Okay, surface area does not affect the vapor pressure. Types of molecules. Types of molecules depends on the intermolecular forces. So when the intermolecular forces are relatively strong, the vapor pressure will be relatively low, and vice versa. Temperature. When there is a high temperature, there are more molecules will have the sufficient energy to escape from the liquid or solid. So when there is a low temperature, fewer molecules will have sufficient energy to escape from the liquid or solid. So for the second part of this presentation, we will discuss about dimensional analysis and modeling. The topics that we're going to cover are dimensions and dimensional homogeneity, dimensional analysis and similarity, the method of repeating variables and Buckingham Pi theorem, and also dimensionless terms. First one is dimensions. Dimensions are a measure of physical variable, for example, base quantities like mass, length, time, temperature, and so on. So primary dimensions are defined as independent or fundamental dimensions from which other dimensions can be obtained. Example of primary dimensions are mass, length, and time. Mass is denoted by the capital letter M, length is denoted by the capital letter L, time is denoted by the capital letter T. Secondary dimensions can be constructed from the combination of primary dimensions. For example, force, pressure, acceleration. Units. Units are the labels for different dimensions in combination for dimensions. For example, kilograms, kg, newtons, N. Brackets are often used around a variable to indicate its dimension. Bracket of power means dimensions of power, and no number is associated with them. Moving on to the next, dimensional homogeneity. Principles of dimensional homogeneity, PDH. The concept where its dimensions of variable on both sides of an equation are same. So if the units are same, the dimension of each term must be same. So given example here where acceleration is equals to change in velocity divided by time. As you can see here, acceleration, its unit is meter per second square, while the right side of the equation, we can times seconds together, so the denominator becomes second square, so meter per second square, and the units on both sides of the equal side will be the same. So PDH is achieved. Every valid equation must be dimensionally homogeneous. An equation could be dimensionally homogeneous but invalid if the equation is not fully balanced. Dimensionally homogeneous but inconsistent in unit is if the units on one side of the equation are different than the other. So as you can see in the given example there, u, where it is the velocity, is equals to initial velocity plus the gravitational acceleration times t, where t is in seconds while the others are in minutes. So we have to fix the variable with the wrong units and use the appropriate conversion to assign the proper units to it. So here we can change the unit of time, which is in second, and divide it by 60 so we can get minutes. Or you can change the other minutes into seconds. Dimensional analysis. Dimensional analysis are the problem-solving method that uses the fact that any number or expression can be multiplied by 1 without changing its value. So what does it mean that sometimes it is necessary to deal with measurements that are very small in size, for example, size of an atom to a very larger size. So it is necessary to convert between units of metric measurements. So converting between metric units is called dimensional analysis. So method of reducing the number and complexity of the experiment variables that affect a given physical phenomena is called the dimensional analysis. So we take a look at this example here. If you had a sample of a substance with a mass of 0.0034 grams and you wanted to express the mass in milligrams, you could use the following dimensional analysis. So the given quantity is the mass of 0.0034 grams. So the quantity that you wanted to find the mass is in milligram. We know that 1 milligram is equals to 10 to the power of negative 3 gram. So expressing this as a proportion or ratio, there is 1 milligram per 10 to the power of 3 grams or 1000 milligram divided by 1 gram. So in order to find the milligrams, we just have to times 0.0034 gram with 100 milligram divided by 1 gram. So we cancel off the unit gram there and we get 3.4 milligram. So as you can see here, there are two types of picture. One is the model and one is the prototype. So basically what this explains is that the model is smaller than the prototype. So in order to save both time and money, these tests are usually conducted with smaller scales, which is the model in this picture, in a white tunnel or water tunnel. So these are a step-by-step dimensional analysis calculation. Step number 1 is identify the given information. Step number 2, identify conversion factors that will help us to get from what our original units to our desired unit. Step 3, set up our equation so that our desired units cancel out to give us desired units. And step 4 is multiply through to get our final answer. And don't forget the units and the significant figures. So this is one of the examples that I've got it. How many inches are in 5 feet? So the given information is 5 feet and we want to convert it into inches. We know that 1 foot is equals to 12 inches. So the conversion factor is 12 inches divided by 1 foot. And then we want to set up the equation. 5 feet times 12 inches divided by 1 foot. And then multiply to 60 inches. So the answer is 60 inches. Second question, another example is how many feet are in 30 inches? So the same formula applies here, but now the conversion factor is 1 foot divided by 12 inches. So that inches can cancel out each other and then we get 2.5 feet. Repeating variables. Repeating variables are any set of variables which they themselves cannot form a dimensionless group. For example, diameter, velocity, and height cannot be arranged in any way such that the dimensions would cancel out, so they form a set of repeating variables. So we know that diameter, we measure it in meter or cm, velocity is in meter per second, and height is also in meter. So no matter how we arrange these three units, they cannot cancel out each other. So that is why they are that is why they form a set of repeating variables. Buckingham Pi theorem. Buckingham pi theorem is used to determine the number of dimensional groups required to describe a phenomenon. The number of dimensionless groups to define a problem equals to the number of variables n like density, viscosity, and etc. minus the fundamental dimensions m like length, time, etc. So as I mentioned earlier, fundamental dimensions are also primary dimensions or independent dimensions. Determining the dimensionless parameters formed by a list of variables, even if in the form of equations, are still unknown. So even if our equations are still unknown, we can still determine our dimensionless parameter. So if there are n variables in a problem and these variables contain m primary dimensions or fundamental dimensions, for example, m, l, and t, the equation relating all these variables will have n minus m dimensionless group. So Buckingham referred to this group as pi groups, and the final equation that we will get is the pi 1 is equals to f in bracket pi 2, pi 3, and so on until pi n minus m. So these pi's are the independent dimensions. So these are the methods of repeating units to determine our Buckingham pi theorem. Step 1 is to list all the variables that are involved in the problem. Step 2, express each of the variables in terms of basic dimensions. Step 3, determine the required number of pi terms, which are also the independent dimensions. Step 4, select a number of repeating variables where the number required is equal to the number of reference dimension. So the number of reference dimension here is actually m. So usually we have the three main m terms, which is m, l, and t. Step 5, form a pi term by multiplying one of the non-repeating variables by the product of repeating variables, each raised to an exponent that will make a combination dimensionless. So this exponent, we can first assume it as a, b, c, and so on. Repeat step 5 for each of the remaining non-repeating variables. So step 6 is basically step 5, but if you have just one pi term, then you don't have to do step 6. You just can skip it. Step 7, check all the resulting pi terms to make sure they are dimensionless. So during this checking time, you can maybe change the m to f in order for you to not to be confused. Step 8, express the final form as a relationship among the pi terms and think about what it means. So after we give our expression, just we can summarize it in a conclusion. So because the step-by-step just now was kind of confusing, so this is an example here. I've got it from the internet. A cylinder with a diameter of d floats upright in a liquid as shown in the figure. When the cylinder is displaced slightly along its vertical axis, it will oscillate about its equilibrium position with a frequency omega. Assume that this frequency is a function of this diameter, d, the mass cylinder m, and the specific weight gamma of the liquid. Determine with the aid of a dimensional analysis how the frequency is related to these variables. If the mass of the cylinder were increased, would the frequency increase or decrease? Let's split it up into a few steps here. So the first one is list all the variables that are involved in the problem. So the question is already given, omega is equals to f bracket diameter, mass of the cylinder, and also specific weight gamma. Step 2, express each of the variables in terms of basic dimensions. The unit for omega is 1/seconds. The unit for diameter is meters. The unit for mass is kilogram. And the unit for gamma is Newton per cubic meter. And in its dimension, don't forget to add the bracket. Step 3, determine the required number of pi terms. So in order for us to determine the number of pi terms, we have to minus n minus m. So we get 1. So there is only one item, meaning that later on, step 6, we can skip it since there's only one item. Step 4, select a number of repeating variable where it is equal to the number of reference dimension. So n repeating variables are the diameter, mass of the cylinder, and also specific weight. Step 5, form a pi term by multiplying one of the non-repeating variables by the product of the repeating variables. Each raised to an exponent that will make the combination dimensionless. So pi is equals to diameter to the power of A, mass of the cylinder to the power of B, specific weight to the power of C, and omega. A, B, C, we just assume it first, okay? And then just substitute in the dimensions. And then we can get m to the power of b plus c, l to the power of a minus 2c, and then t to the power of negative 2c negative 1. And then we just assumed it again. So m to the power of 0, l to the power of 0, and t to the power of 0. And then we just have to do the algebraic. So b plus c is equals to 0, a minus 2c is equals to 0, negative 2c minus 1 is equals to 0. So if we solve the last equation there, we can get c is equals to negative half, and then just substitute in the other two values to get a and b respectively. And then after we get our exponents, just substitute back into our original pi term. Omega divided by the diameter, square root of mass of the cylinder divided by specific weight. Step 6. Repeat step 5 for each of the remaining non-repeating variables. Since we have one pi term only, so we can skip this. Step 7. Check all the resulting pi terms to make sure they are dimensionless. So one good way to do this is to express the variable in terms of capital letter F, L, and T if the basic dimensions are capital letter M, L, T were initially used, or vice versa. So when we check it, we can get F to the power of 0, L to the power of 0, and T to the power of 0. The dimensionless function is omega divided by diameter, square root of mass divided by specific weight, which is equal to constant C. And the last step is to express the final form as a relationship among the pi terms and then think about what it means. So since C is our constant, so we make omega as our subject because it is stated in the question there that the omega will be our function. Omega is equals to constant times the diameter square root of specific weight divided by mass. So in conclusion is that when m increases, omega will decrease. Since m is in the denominator, any increase in m will cause a decrease in omega. If only one pi term is involved in a problem, it must be equal to a constant. Last but not least, dimensionless terms. Dimensionless terms is a quantity to which no physical dimensions is assigned. So it is basically a scalar quantity. Non-dimensionalization is the removal of units from physical quantities by a suitable substitution of variables. While non-dimensionalized equation is when each term in an equation is dimensionless. So that is it for my presentation. Thank you.